Today we're going to continue talking about hypothesis testing, and we're going to do so by finishing up talking about testing a claim about standard deviation or variance. So we'll be working on how we can do a formal hypothesis test of a claim made about a population standard deviation or population variance, and we'll be using the chi-square distribution to do this. So again, our formal objective is to conduct a hypothesis test of a claim about a population standard deviation or population variance. And our notation has not changed from when we first saw this stuff. So we have n for sample size, we have s as our sample standard deviation, we have sigma as our population standard deviation, s squared for our sample variance, and sigma squared for our population variance. So we need to check a couple of requirements in order to do a hypothesis test about standard deviation or variance. The first is that the sample is a simple random sample, and the second one is that the population has a normal distribution. This is going to be a strict requirement for us. This says that it's a fairly strict, we're not going to get into that wishy-washy gray area. It's going to be a strict requirement that it needs to be a normal distribution. So our test statistic we'll be working with is chi-square. So we worked with this when we were doing confidence intervals about standard deviations and variances, and it's back again for us doing hypothesis testing about standard deviation and variances. So we have chi-square equals the quantity n minus 1 times our sample variance divided by our population variance. We're going to round that to 3 decimal places. So we'll find our p-values by using technology or table A4. Again, we're not going to use technology, but we will be making sure that we can read the output of technology. And our degrees of freedom is going to be n minus 1. For our critical values, we will also be using table A4 with our degrees of freedom being n minus 1. Now, when we are talking about different methods for doing this, the p-value method, the critical value method, and the confidence interval method are all going to be equivalent in this case. So they're all going to lead to the same conclusion. So just different ways to get to the same conclusion. So the chi-square distribution, just a reminder about this distribution. So all of the values of chi-square, they're non-negative. And the distribution is not symmetric, it's skewed right. Also, for each degrees of freedom possible, we're going to have a different chi-square distribution. The higher the degrees of freedom, the shorter and fatter the distribution is going to be, the more bell-shaped really that it gets, but it's still always going to be skewed right. Now, the critical values are going to be found using table A4, using degrees of freedom n minus 1. So, just an important note about table A4, the critical value of chi-square in the body of the table. All right, so we're going to be looking for chi-square values in the body of the table. We'll be using the row that is corresponding to our degrees of freedom. And across the top, the areas are going to be given. Those areas across the top are the cumulative area to the right of the critical value. And again, this is a distribution that doesn't show you a picture to remind you of that, but it is labeled that it's the area to the right. So let's take a look at an example. Let's use the p-value method to determine, do supermodel heights vary less? So listed below we have the heights in centimeters for the simple random sample of female supermodels. So we're going to use a 0.01 significance level to test the claim that supermodels have heights with a standard deviation that is less than 7.5 centimeters for the population of women. Does it appear that the heights of supermodels vary less than heights of women from the population? So there we have our sample. So first thing first, we need to check our requirements. So the first requirement, they told us that it's a simple random sample, so we've got a check mark there. Our second thing that we need to check is we need to check for normality. So here's a normal quantile plot, and we can see that there's nothing really extreme there, and it fits that straight line pattern. And so we can conclude that it is in fact normal. And so if we were to use technology, we go through and we would put in what we were looking for, and we would get a value. They would say the p-value is less than 0.0001, right? And they tell us that our chi-square statistic is 0.907 if we round it to 3 decimal places. So technology can do this for us, but again, we're just reading the output of our technology. Make sure that that box makes sense to you. And now we're going to move on to talk about all the steps that went into setting up to be able to use the technology and how we would use table A4 to help us out. So step 1, we need to look at the claim that's made. It's the standard deviation is less than 7.5 centimeters. So symbolically, we represent that with sigma less than 7.5 centimeters. So then step 2, we need to take the opposite of that. So that would be that sigma is greater than or equal to 7.5 centimeters. Then we identify our null hypothesis by looking for where the equal sign is. So that'll be that sigma equals 7.5 centimeters. And our alternative hypothesis is identified by being the one that doesn't have an equal sign with it, which would be our claim that we were looking to test, that sigma is less than 7.5 centimeters, that original claim. So now that we have our null hypothesis and alternative hypothesis, we're going to move on. Step 4, is to identify the significance level. Identifying the significance level, they told us that we need a 0.01 significance level. So alpha is going to be 0.01. For step 5, the claim is made about the standard deviation, about sigma. So the chi-square distribution is the test statistic we need to be using. Now, step 6. All right. This is, again, showing you what's going on with this technology display. So StatCrunch display shows the test statistic is 0.907, and it shows the p-value less than 0.001. All right, so we would say because the p-value is less than the significance level of alpha equals 0.01, we reject the null hypothesis, and we would interpret it saying there is sufficient evidence to support the claim that female supermodels have heights with a standard deviation that is less than 7.5 centimeters for the population of women. It appears that the heights of supermodels do vary less than the heights of women in the general population. So we've done all this work to do this. All right. So if we were using the p-value method and using our table, what we would need to do is calculate chi-square, which we're going to look at how to do when we talk about the critical value method. And then we would use table A4 to find the p-value associated with that chi-square value. So let's talk about how we calculate chi-square. All right. So here we have our population standard deviation that we're testing is 7.5. So we'll be plugging 7.5 in for sigma. So 7.5 squared will become our denominator when we're calculating chi-square. And our sample size, we could count, there are 16 heights in our sample size. And our sample standard deviation, we can calculate that from those values that were given. And if you do that, you get 1.843909 centimeters. This would be a great opportunity to double check that you're comfortable calculating a sample standard deviation, going back to those values. So once we have all of those values, we plug them all in and we do this arithmetic, probably use a calculator to help us out, and we find our chi-square value of 0.09 or 0.907. So this is the same value that the technology display showed us as well. So then we go to our table A4. So with the critical value method, what we're doing is we're looking for the chi-square value that has 0.01 to the left as the area to the left of it. Now, this is because our alternative hypothesis is that our standard deviation is less than the 7.5 centimeters. So it's a left-tailed test that we're working with. Now remember, our table gives us areas to the right. So we're looking for, in the 15 degrees of freedom row, we're looking for the area to the right of 0.99. And if you go and find that value, then we have a critical value of chi-square equals 5.229. Right. Our chi-square value of 0.907 is less than that one. So it is in that critical region, which allows us to decide we're going to reject the null hypothesis. We'll get back to that conclusion, what we say, in just a second. But if we were using the p-value method in table A4, you would go and you would look in the 15 degrees of freedom row, and you would locate where 0.907 would fall in the spectrum of chi-square values given. And then you would approximate what the p-value is based on that. To find the exact p-value, we need to use technology always with this, but we can approximate where it would be. All right. Critical value method, we don't need technology to find it at all. We can find our critical value and we can see how our chi-square value relates always. All right, so in step 7, we reject the null hypothesis because the test statistic falls in the critical region. We conclude that there is sufficient evidence to support the claim that supermodels have heights with a standard deviation that is less than 7.5 centimeters for the population of women. All right. Now, this still says that we're talking critical value method, but we're not, all right? The title of this should actually say confidence intervals. So let's talk about confidence intervals. First, we're going to select the correct confidence level, all right? So when we're looking at confidence intervals, we need to do the translation that's going on. So because the hypothesis test is a one-tailed test, a left-tailed test, and the significance level is 0.01, we're going to use the confidence level of 0.98. All right, a 0.98 confidence level is going to put 0.01 as the area in both of the tails from that confidence interval. All right, so we're looking for a 98% confidence interval then. So we go through, and this is just like it was in the previous chapter when we were putting together confidence intervals. We can use that sample data that was listed in the example. We can construct that 98% confidence interval estimate. So we're going to find what we know n is 16. We know our sample standard deviation is 1.843909. And again, we got that by calculating it from the sample that was given. And then we can go into table A4 and we can find our chi-square left and our chi-square right value. So remember, the chi-square left value is the one that has 0.01 to the left as the area to the left. And the chi-square right value, or chi-square sub r, is going to be the one that has 0.01 as the area to the right. So then we plug those into our formula for finding our confidence interval for our standard deviation. It's the same as the one for the variance, except for we have square roots over top of everything to get rid of that squared. And when we do that, we get 1.3 centimeters as a lower bound and 3.1 centimeters as an upper bound. So we have our standard deviation being between 1.3 centimeters and 3.1 centimeters. So with this confidence interval, we can support the claim of our alternative hypothesis that the sigma is less than 7.5, so standard deviation is less than 7.5 centimeters, because all of the values of the confidence interval are less than 7.5 centimeters. And that's all there is to this. So get some practice in, and you're going to do awesome.